Hello, everyone. My name is Yuankang, and I'm currently a master student at Durham University. Today, I'm going to present a subgrid turbulent dynamo model for cosmic magnetism. But first, let me say a few words about cosmic magnetism. The initially a weak magnetic field is predicted by BMM battery theory in shocks and ionization fronts. The typical strength is about 10 to the minus 20 Gauss. And nowadays, radio observations show that the magnetic field strength in the Milky Way is about 10 microgauss, and similar for the nearby galaxies. So you can see the huge gap between 10 to the minus 20 and 10 to the minus 6. It means that we need an efficient amplification mechanism, which is usually called the dynamo process. There are two types of dynamo. A small-scale dynamo is driven by a turbulent motion and it features efficient amplification, while the large-scale dynamo produces magnetic fields ordered on scales larger than the flow scale. Here is an example of a turbulent dynamo. The field line is stretched and twisted due to the fluid motion, and then the field line is folded against itself. And finally, magnetic reconnection kicks in and the field line merges. And then the field strength becomes twice the initial value. With this method, you can have very efficient amplification. In our simulation, we are modeling the baryonic matter using the 4 ideal MHD equation with the cooling and heating. And the solenoidal constraint is preserved by using the constrained transport method. And these equations are solved by using AMR technique based on the second order Goodenough scheme. In mean field electrodynamics, we usually consider a mean field and a fluctuation term. So here we decompose the velocity and magnetic field into a mean part and a fluctuation term. And then we plug these two terms into the induction equation in the previous slide. And then we average the whole induction equation to get equation 7. In equation 7, we have a term ET, which is a turbulent electromagnetic force, and it's given by the mean value of the cross product of the fluctuation terms. Now the problem becomes more like a standard closure problem. We have to come up with a way to relate ET to the mean magnetic field. And here we simply relate them by a alpha tensor. And if the turbulence is homogeneous and isotropic, we can say that the alpha tensor has a diagonal form and can be rewritten as a scalar alpha times a unitary tensor. And finally, we propose the expression for scalar alpha to be equation 9. Here in equation 9, the sigma t is the turbulent velocity dispersion, and the rho sigma t squared is the unresolved turbulent energy given by the turbulent subgrid turbulence model in Ramsey's code. And to simplify our discussion, we define the saturation ratio R to be the ratio between the magnetic energy and the turbulent energy density. The R is usually between 0.1% and 50% in driven turbulence box simulations. And then the expression for scalar alpha t becomes equation 11. As you can see, the alpha t will be approaching 0 as R is approaching epsilon. And epsilon in our simulation is chosen to be 10 to the minus 3, which corresponds to the saturation ratio 0.1%. So the whole picture is simple. The magnetic field is simply amplified by the subgrid turbulence until it reaches saturation, and then the field evolves by the resolved motion, and And the simulation, we are running a cosmological MHD zoom-in simulation using the AMR called Ramses. So first, we have an n-body simulation with a huge box size using the standard lambda CDM cosmology. And then we select Milky Way-like halos, and we generate initial conditions for increased resolution runs. Our simulation involves full subgrid physics, including star formation, supernova feedback, unresolved turbulence, and so on. The initial magnetic field is set to be 10 to the minus 20 Gauss along the z-axis in the simulation box. Okay, let's move on to the results part. First, we should take a look at the effects of the epsilon parameter. Here, I'm showing you the ratio between magnetic energy and turbulent kinetic energy density versus the gas density within 1 virial radius at redshift 0. We can see most of the region has reached saturation set by the epsilon parameter. The resolved motion then amplified the field by 4 orders of magnitude, but not much more. And in our simulation, we set the initial magnetic field to be 10 to the minus 20 Gauss. Due to the frozen-in behavior of the ideal MHD, when the field expands and collapses because of the gravity, the magnetic pressure will scale as the rho to the 4/3. The figure here shows the 2D mass-weighted magnetic pressure against the gas density within 10 virial radii. We can see a region following the ideal MHD scaling. When the gas collapses and forms a star-forming disk, the subgrid dynamo starts to amplify the field. We can see the effect in the 2 upper branches. And now, let's look at the galaxy at high redshift 4. The figures show the projected gas surface density, density-weighted magnetic field strength, and density-weighted metallicity. The white solid circle here indicates 1 virial radius, and the white dashed circle indicates the galactic disk. The field strength drops from 100 microgauss in the center to 1 microgauss in the halo. The value is greater than a typical galaxy at lower redshift because the turbulence is higher and the outflows are much stronger in high redshift. The metallicity plot confirms that the halo magnetic field comes from the metal-enriched materials in the outflows. At redshift 0.2, we have a nice disk. So the field strength is about 100 microgauss in the nuclear region and 10 microgauss inside the disk. And in the circumgalactic medium, the field strength is about a few nanogauss. And finally, to understand the topology of the magnetic field, we decompose the field in cylindrical coordinates. We can see that the magnetic field is dominated by the toroidal component with a typical strength of around 10 microgauss. The orientation of the toroidal field is the same across the disk. However, the field strength of the vertical and the radial components is much weaker than the toroidal field. They also exhibit small-scale structures, with the field orientation flipping multiple times at a given radius. Okay, in summary, we have developed a subgrid turbulent Dynamo model in Ramses code and tested it in a cosmological zoom-in simulation. The weak seed field is amplified by the subgrid Dynamo model efficiently in the turbulent environments. And then the field is further amplified by the resolved motion. I hope this talk is helpful to your research, and thank you for listening.